Okay, so today's lesson will be focusing on finding the distance between points and lines and lines and lines and lines and planes and points and planes. All kinds of different combinations. However, they will all use three different formulas. So we're going to start off with how to determine the distance between a point and a line in 2D. Okay, so that's R2 right here, so we're going to look at 2D. Now, when we're finding this distance, we're actually finding the perpendicular distance between the point and the line. The reason why we're finding the perpendicular distance is because it's the shortest distance. So if I were to find the distance from this line, this point to this line over here, this is not the value I'm finding. It's D that I'm finding. This will be the shortest distance because it will always be the perpendicular distance. So if we look at our formula, D is equal to the absolute value of AX naught plus BY naught plus C all over the root of A squared plus B squared. Okay, so this is created from your distance formula that you're familiar with. However, we need to know the standard form of our equation of the line in 2D. So standard form is okay. Now, if you'll notice on your sheet right here, you had a 5. So make that change so that you have a 9. And the reason why, if it were a 5, these lines would intersect, and then the shortest distance between them would be 0. So we're actually looking at the distance between these parallel lines. And I know they're parallel because my direction vectors are multiples of each other. All right, so we're going to start off. I'm going to just arbitrarily decide to take the first line, and I want to make that into y equals mx plus b. So my slope is going to be 12 over 9. So I'm going to reduce that down to 4 over 3. When I do that, I then get y equals 4 over 3x plus b. So we're going to sub in our point. So I have 0 equals 4 over 3 multiplied by 1 plus b. So negative 4 over 3 equals b. So that means my equation is y equals 4 over 3x minus 4 over 3. This is close to standard form, but not quite. I'm going to get rid of the fractions. So I get 3y equals 4x minus 4. So then I will have 0 equals 4x minus 3y minus 4. So I needed this form of the equation because this here will be my A, the negative 3 is my B, and negative 4 is my C. So now that I have that information, I can now find the distance using my formula. So D equals the absolute value, and it's absolute value because distance is a positive value. So I have A, which is 4. The x naught is the point. So the other point that I'm looking at is negative 1. So that's what I'm going to put for x, minus 3 multiplied by 2, and then plus c, which is going to be minus 4. And then that's all over the square root of a squared. So I have 4 squared plus negative 3 squared. So when I do this here, I have negative 4 minus 6 is negative 10. And then I have minus 4 up there. So negative 4 minus 6 is negative 10. So this is negative 14 over 5. So the distance is 14 over 5 units. So in 2D to find the distance, one of the lines, you need to know the scalar equation, and then you're going to use the point for the other line, and you're simply going to substitute in. Now the lines have to be parallel in order for this to work. Otherwise, your distance will be 0 because it means they will be intersecting or coincident. Okay, so now in 3D, because we don't have the scalar form of the equation of a line in 3D, we can't use that same formula. So it's been derived that the distance is equivalent to the magnitude of the cross product between our direction vector and another vector that's created between a point that's on the line and the point that you're looking at. So this formula, it will be given to you. So M is our direction vector, and then QP is a point on the line and another point. So you'll have to generate that vector, and we need to do the cross product. So as per usual, we're going to look at an example. So I know right here, I have a direction vector at -4, 5, and 20. Point Q is this value right here. So when I create vector QP, I have 0 subtract 2 to get -2. I have -1 subtract 1 to get -2. 0 subtract 0 to get 0. So those are the values that I have for QP. So I need to figure out the cross product of M cross QP. So when I line my stuff up, -4, 5, 20, -4, 5, 20, -2, -2, 0, -2, -2, 0. So cancel this out. So I have 5 multiplied by 0, so that's 0 minus -40, so that gives me 40. Then I will have, so that's these two. 20 multiplied by -2 is -40 minus 0, so I have -40. And then I have -4 multiplied by -2 is +8 minus -10, so that gives me 18. So this here is the cross product between M and QP. The distance is equal to the magnitude of the cross product over the magnitude of the direction vector. So I have the square root of 40 squared plus -40 squared plus 18 squared all over. Our direction vector will be the square root of -4 squared plus 5 squared plus 20 squared. So when I do that, this is going to be 2 root 881 over 21 units. If you change it to a decimal, it's okay for this, so you can leave it as 1 decimal place. However, the more exact you leave it, the better off you are. So that would be the answer here. As always, make sure you check my algebra to make sure that I didn't mess up. Okay. All right, so now the distance between a point and a plane in R3. This formula looks a lot like the distance between a line and a point in R2. However, in 3D, whenever we have a scalar equation, it represents a plane. So once again, the A, the B, the C, the D, those are the coefficients in the scalar equation. And then X naught, Y naught, Z naught, those represent the point. So here's a standard question. Determine the distance between the point and this vector. So I know A is 4, so we have 4 multiplied by 10 plus 2 multiplied by 3 plus 1 multiplied by -8 plus -16 all over the root of A squared, so that's 16 plus 4 plus 1. So my numerator, I have 40 plus 6 is 46. So 46 subtract 8 is 36. No. 46 subtract 8 is 38. Subtract 16 is 22 over root 21 units. So very much a plug and play situation. So as long as you have the scalar equation and a point, you can find how far apart those items are. Unfortunately, it's not always as easy as per usual. So what happens if we have 2 parallel planes? Well, it's not that much harder. If we have 2 parallel planes, any point on one plane will be the same distance on the other plane. So we're going to start off by finding a point. So the easiest point to find, as always, is one of the intercepts. So I'm going to get the x-intercept for pi 1. So I have 2x minus y plus 2 multiplied by 0. I'm going to put that 4 over right away, negative 4. So 2x equals negative 4. So x equals negative 2. So that means I have a point at negative 2, 0, 0. Now that I have that point, I'm ready to go with my formula. So a is 2, x is negative 2, plus b is negative 1, y is 0, because that's the y coordinate of our point, plus 2 multiplied by 0, plus 16, all over square root of 2 squared plus negative 1 squared plus 2 squared. So when we do that, the numerator, we have negative 4 plus 16 gives me 12. 2 squared is 4, 8, 9. Square root of 9 is 3. So this one equals 4 units. You could use any point on one plane and use the other plane as your A, B, C, and D value. If you don't believe me, try it. All right, we got one last example. All right, so determine the distance between the skew lines. So remember, the distance we're looking for is the shortest distance possible, which means it's the perpendicular distance. For these skew lines, there's a few ways of doing this question, but the easiest way is to think of those skew lines as a plane. And you're probably like, well, Miss, you told us before skew lines can't give us a plane. Well, we're not actually using both lines. We're just going to be talking about the direction vectors. So I'm going to create a plane using the direction vector from here, the direction vector from here, and I'm going to use this point. Okay, so when we have lines, how do we get a plane? We need the normal. So the normal is going to be 2, 5, 10 crossed with negative 1, 11, and 8.5. So when you do the cross product for this here, you're going to get negative 67.5, negative 27, and 27. Once again, always check to make sure you're getting this answer. So when you do the cross product, that's what I ended up with. So from here, I now know that I have negative 67.5 x minus 27y plus 27z plus d equals 0. So I need d. Now that I have this here, I am going to substitute in the point, positive 2, negative 1, 7. So negative 67.5 multiplied by 1 minus 27 multiplied by, actually this here should be a 2, negative 1. Okay, so we end up with, when I do all that, 81 plus d equals 0. So that means d equals negative 81. So our equation is negative 67.5x minus 27y plus 27z minus 81 equals 0. So you're probably like, well, how is this happening? So you have your plane, that's right here, and you have this line that's above. So that's this line right here. So the line that's above is right here. So if I pick this point, I'm trying to find this distance right here. If I pick this point over here, it's the same distance no matter what we look at because they're all perpendicular. So I have d equals absolute value of negative 67.5 multiplied by 4 minus 27 multiplied by minus 21. And then I have plus 27 multiplied by 6 minus 81 all over square root of negative 67.5 squared plus negative 27 squared plus 27 squared. Now, because we have decimals here already, we're going to use our magical calculators and find 4.9 units as our distance. So anytime you're looking for the distance between skew lines, the easiest way is to think of it as one line and then create a plane using both direction vectors. So hopefully this makes sense. And if you have any questions, come see me.